This new section is section 13.3a on partial derivatives. So I'm going to show you here this little diagram that has a surface in 3D space. Notice x, y, the x, y, and z axis. And we have a point here in blue as our point on the surface. We have tangent lines drawn through them. So this curve right here going from the top right to the bottom left is a curve in the plane y equals to y naught. So basically the variable y is held constant and we have a tangent line. This is called the slope f sub x, which is actually what we have as our partial derivative. And over here, if you notice, there's another tangent line that's being drawn, but x is held constant in this case, so this would be called f sub y. So here's our definition of our partial derivatives. And notice we now have some function z equals to f of xy. So we have what are called the first partial derivatives. The notation that we use will be f sub x, or here's a new notation. It is not the same df dx as you were used to, but sort of a different symbol. It's the partial derivative symbol, and it looks like a backward 6, so drawn like this. And it's also read the same, df dx. Here's our formal definition for the partial derivative using limits. Below it we have f sub y, or df dy, and again its definition using limits. So it's going to be really easy for us to apply, so I want you to look at this first example and how we do it. I have my function f of xy, and it's x squared plus 3xy plus y minus 1. So I want to find df dx. So when you're calculating these partial derivatives with respect to whatever variable, in this case x, I want you to think about y as being constant. So when we calculate this, the only variable is x now, so the derivative of x squared with respect to x is 2x. The derivative of 3xy, remember, our variable is x, so y is constant, is going to be 3y. And then that's it, because y is constant, so the derivative of that is 0, and negative 1 is also constant. Now trying df dy, here x is going to be constant, so when we calculate this, with respect to y, all we're going to have is 3x plus 1. Let's try another example. This is our alternate notation, f sub x. This is the exact same thing as saying df dx. Because y is constant, x is our only variable. The derivative of sine is a cosine. And then we have the chain rule, so we also have to multiply by y. And we already have one out there, so it now becomes y squared. Now f sub y, that's like saying df dy. So because x is constant, we actually have to use the product rule here. So the derivative of y times sine of xy will simply be sine of xy. And then we'll have y times the derivative of sine of xy, so that's going to be cosine of xy. And then we have the chain rule, the derivative of xy, x is constant, so we're going to have an extra x in here. So let's try another example. F of xy equals to 2y over y plus cosine x. So you could even think of this as 2y times y plus cosine x to the negative 1 power. So finding f sub x, we simply have the derivative of this latter part, so negative 2y times y plus cosine x to the negative 2 power, and then our chain rule, the derivative of cosine, which is negative sine x. So simplify this stuff out. We have 2y sine x all over y plus cosine x quantity squared. Now let's take a look at f sub y. X is constant. We can go ahead and use the quotient rule, the derivative of the top times the bottom, so 2 times y plus cosine x minus the derivative of the bottom. Now remember x is constant, so all I care about is this y over here, times the derivative of the top, all over the bottom squared. Now simplify this stuff out. We have a 2y and another minus 2y over here, so all we have is 2 cosine x over y plus cosine x quantity squared. I want to find dz dx, here I'm just using the notation with z instead of f for my function, still with respect to x, so y is constant and z is our variable. So I've got y times dz dx minus, now the derivative of a natural log is 1 over z, z is my variable, so I need another dz dx over here, equals to the derivative of x with respect to x is 1, and y is constant, so that part of it is a 0. I'm solving for dz dx, so I need to factor that out. So I have y minus 1 over z equals to 1. So dz dx equals 2. I can actually combine these by giving them a common denominator, z over yz minus 1. We can also find partial derivatives at specific points. So let's quickly find the partial derivatives, f sub x. With respect to x, this is going to be the product rule. So e to the x squared y plus x times, now e to the x squared y times 2xy. At the point 1 ln of 2, we're going to plug in 1 for x and ln of 2 for y, e ln of 2 plus e ln of 2 times 2 ln of 2. E to the ln of 2 power is equal to 2, so I have 2 plus 4 ln of 2. Then we have f sub y, x e to the x squared y times the derivative of my exponent, which is x squared. So I have x cubed e to the x squared y. At the point 1 ln of 2 is going to be e ln of 2, or 2. So these are what are called first partial derivatives, and we also have second partial derivatives. The notation that you need to be familiar with for second order partials is this. It's going to be d squared f dx squared and d squared f dy squared. And our notation here is going to be f sub xx and f sub yy, because this is the derivative with respect to x of df dx, and also the derivative with respect to y of df dy. Now these are called the second order partials, and we also have what are called the mixed order partials. So these over here are a little bit different in that we have the derivative with respect to x of df dy. So this is actually written d squared f dx dy, or we can write it out as f sub yx. Now I need you to notice the order with which I've written these subscripts, and paying attention to the parentheses can help you understand why this is f sub xy for the second one. So these are called the mixed order partials and the regular second order partials. Let's just do one example. F of xy equals to x cosine y plus y e to the x. So I'm first going to find df dx, which is going to be, now y is constant, so I just have cosine y plus, now remember y is constant, so this is y e to the x. I have df dy. Now tell yourself x is constant, so the derivative of x cosine y with respect to y is going to be negative x sine y. Remember, with respect to y, x is constant, so now this is e to the x. So now I can find d squared f dx squared, so with respect to x one more time, is going to be y times e to the x, and taking the derivative of this one the second time with respect to y, negative x cosine y, and x is constant, so that second part is 0. Now let's find the mixed order partials, so that means I'm going to find d squared f dy dx, and over here I'm going to find d squared f dx dy. So in this case I have negative sine y plus e to the x, and over here taking it with respect to x, I have negative sine y plus e to the x. Now notice here these two mixed order partials are the same. This is always going to happen when all of your partial derivatives and the mixed partials are continuous.